Yeah, okay. So first of all, I would like to thank Professor Iman for this invitation. It's actually a pleasure to give this talk, and I think this is a really great initiative, especially during these moments we are suffering. So as Iman was saying, I'm going to talk about mean field type games. So another way to interpret these games is as risk-aware interactive decision making. And the main objective in this talk is to present how we can solve these class of problems in an easy way. So we want to make it easy. So throughout the presentation, I'm going to be talking about risk terms. So let me start by introducing some concepts. So let's suppose you have some money you want to invest. And to do that, let's suppose you have two options. So these options are given by asset number 1 and asset number 2, as we see in this picture. And the thing is that the assets are normally characterized by two main parameters. So these parameters are the expected return, and we also have the standard deviation. So based on these parameters, we can make decisions about where to put our money. So to make it simple, let's suppose that in both assets, we have the same expected return that is denoted by R. But in contrast, we consider that the asset number 2 has a higher standard deviation. So we denote that by sigma 1 and sigma 2. So the important thing here is that the actual return is going to belong to these ranges, depending on the selection we make. And the message in this slide is that in asset number 2, we can potentially have a higher return, but at the same time, we're going to have more risk associated to it. And that's because of the standard deviation. So this problem is known as a diversification problem, and it was introduced by Professor Harry Markowitz, that is in this picture on the left side. And the objective is summarized by means of this expression. So what we want is to maximize the expected return, but at the same time, we want to minimize the risk. So we want to minimize the volatility. So let's consider this picture. So we can summarize the scenario in which we are. We have the asset number 2 with a corresponding risk term and with a respective return. So the same thing we have for asset number 2. Okay, so one might think that if we want to minimize the risk at the time we invest in this portfolio problem, we might decide to put all our money in asset number 1, and that's because we can minimize the risk. But actually, that's the interesting part about the contribution by Harry Markowitz, which is that actually there's a combination in which we can do a resource allocation, or in which we can divide our money such that we can minimize the risk. So this is the problem that Harry Markowitz solved. So now the question is, how can we use these concepts and to apply them in control theory or in engineering problems in general? So to illustrate this, let's consider this simple control problem. So let's suppose we have a temperature controller. So we might have some disturbances that affect our system, and we need to design a controller that just drive the temperature to a desired level. So in this particular example, let's suppose that our reference is given by 23 degrees Celsius. And then we have two options. So there are two different controllers that can make this job. So we have the behavior given by the blue controller and the behavior given by the red controller. So if we check the expected value or the expected behavior of the temperature, then we might prefer the controller with blue color. And that's because we don't have steady state error. We have shorter settling time. And if we check the overshoot, we can definitely say that the blue controller behaves better. But now, when we stop checking the expected behavior and we see the actual behavior of the temperature, then we might change our mind. And that's because the blue behavior is very noisy. It oscillates a lot. So when we see the real behavior of the temperature, we might prefer the behavior given by the red controller. And that's because of the volatility we see associated to it. And that's highly related to the previous slides I presented to you. So we can see in this picture that the red behavior has a smaller volatility with respect to the blue one, and then we might prefer that one. And that's what we want to do. We want to quantify the risk and we want to minimize it. So this is how we can actually use these concepts in control theory. So as a motivation, we have many applications where we can apply mean field type control and game theory. And that's because we can find a lot of uncertainties in many applications. So if we see the power systems, we realize that we might have a lot of uncertainties associated with the renewable energy resources. So we have uncertainties associated with the behavior of the wind or the sun and so on. And besides that, we have uncertainty related to the demand we might have in the system. If we check now the traffic systems, we may have many uncertainties regarding the incidents we may have on the way. So I don't know if this has ever happened to you, but when we check the shortest path, maybe using Google Maps, and we take that path, it might happen that an incident occurred on the way, and then it turns out that it's the longer instead of the shorter. So if we have information about the distribution of the incidents on the way, we can apply risk minimization. In the social networks, we have uncertainties related to the information that we find there. We have uncertainty related to the reputation of people we follow and so on. And we might have also some malicious users in the social networks. In the next application is actually very related to the first part I presented to you. So we have uncertainties about the price evolution of the currencies. So we can see these very abrupt changes that some currencies have. So we might want to minimize the risk associated to it. Regarding the water systems, then we have uncertainties related to the demands as well. We don't really know the demand, the actual demand. We have an estimation of the average behavior of the demand, but we don't really know how it's going to behave. And we have prices also associated to it because we need energy to operate the actuators, in this case, the valves and pumps. And then we have also uncertainties there. And finally, we have the district heating networks. So in these systems, we have basically a mixture of power systems because we need the energy to manage the temperature. And we normally use water in these type of systems. So as you can see, we have a bunch of applications in which we have uncertainties. And then this is a motivation to try to quantify and also minimize the risk. So let me now tell you about two different approaches that we have in order to design risk-aware controllers or games or mean field type games and controllers. So the important thing is that in this class of controllers, we care about the distribution of the variables of interest. So we're going to check also the distribution of the system states and the distribution of the control inputs. So on one hand, we have the non-atomic games. So in this class of games, we assume we have a large number of decision makers or agents or players in the game. And the thing here is that since we have a large number, then the decisions of a single player are negligible. So one player is too tiny that actually cannot have an impact over the game. So there are some examples of this class of games like population games. So when we have a large number of agents in a population, and so on. And in this perspective, under these games, we normally compute the expectation by means of the empirical expectation. So this is actually quite related to aggregated games as well. And on the other hand, we have the atomic games. So under this approach, or under this class of games, we have a finite number of players. And then we can check the distribution of the behavior of the states and the control inputs. So we use the probability measure of the states to compute the expected behavior. So in this slide, I would like to say, of course, that there are many researchers working on the field in both approaches, in non-atomic games and also in the atomic part. So here below, I present some important names that work on this, like Keynes, Juan Malamé, Tamer Bashar, Ben Swossan, and so on. And there are some people. There are some people also working on the discrete time approach. Okay, so this is an example of a problem statement of a mean field type controller. So this can be seen also as a game in which we have only a unique decision maker. So we have a cost that we want to minimize, and this cost is of mean field type, in the sense that we have a mean field term that is denoted by M. And then we have a terminal cost that is denoted by H, and a running cost denoted by this L. And then we're interested in minimizing the expected cost subject to this stochastic differential equation. So the B term is known as the drift, that it's state dependent, it's control input dependent, and it's also mean field dependent. So we might have these three terms in the drift. And the same might happen in the diffusion term. So here B, capital B, denotes the standard Brownian motion, and we can compute the expected values by using the probability measure of X. So how can we solve this class of problems? So one way is to solve this system. So this is a backward-forward partial-integral differential system. And in general, it's very complex to solve because we have a coupling between the evolution of the probability measure of the states, and we also need to solve the Hamilton-Jacobi-Bellman equation. We have some boundary conditions and the terminal time, and then we might have information about the initial distribution of the states. And then there are many works studying conditions under which we can solve these type of problems. And the main references for that are the ones in here. But I would like you to keep in mind this system, because I'm going to refer to it later on, because the idea is to solve these kind of problems in an easy way, avoiding to go over these PDs. So what I presented before was related to control part, but now we want to have multiple decision makers. So we want to talk now about game theory. So the idea is that we know many game theoretical solution concepts. So we have the adversarial games in which we have a min-max problem. We also have the Birch games. So this can be interpreted as a mutual support, which is very interesting. It's like that I act in a way in which I can minimize your cost, and you you apply actions pursuing to minimize my cost. So it can be seen as mutual support. And that's interesting because we hardly ever see that in the systems, the mutual support. We also have the Nash solution in the context of non-cooperative games. And we also have the class of games in which we have a sequential order in the decisions that are made. So when we have two layers, we talk about Stackelberg games. And when we have more than two, then we can generalize in a hierarchical game. So the idea is to get these game theoretical solution concepts and then add risk terms to those games. So the idea is to use the results or the problems that Harry Markowitz worked on, and then combine these two areas. So this is a risk-aware interactive decision-making, or risk-aware game, or mean field type game as well. So in here, I present the case in which we have a finite number of decision makers. So we have n decision makers. In this diagram, I present with red color the players, and then they can affect the system state evolution that we present here with the blue color. And we have some, we have a Brownian motion affecting the evolution of the state, because we have a stochastic differential equation. So we see here that all the players are interested in minimizing a cost that is of mean field type. So it means that it has some risk terms associated to it. So we have variance terms in this problem. Of course, it's important to mention that we might consider other type of risk terms like skewness or kurtosis, or even higher order terms when we have risk sensitive problems. But in here, I'm going to present the variance, the variance problem. So it might look at first impression that all these costs are independent to each other, but actually we have coupling through X, because all the players can affect the evolution of the system state. So this is a particular, this is a problem statement for the game case now. So I have here the mean field terms expressed as the expected value of the system states and also the control inputs. And then we have here that in the drift and in the diffusion terms, all the players are affecting the evolution of the system state. Okay. So with this problem in hand, now we can define the solution concept for the non-cooperative games, which is the Nash equilibrium. So prior to doing that, let me introduce the best response. So a feasible control input is a best response if it minimizes the cost of the corresponding player, given the decisions of the others. So given the decisions of other players, the ith player can do his best. And then a Nash equilibrium is given by a strategic profile in which all of them are best response to each other. So in other words, it's a situation in which the players have no incentives to change that strategic selection, because it's the best they can do. And that's how we compute the Nash equilibrium in this class of games. That actually is the same definition we have in differential games or LQ games. But now we have risk terms also in the cost. So the question now is if we can solve these kind of problems without having to solve the partial integral differential equation system. And the answer is yes. There are a family of problems in which we can find semi-explicit solutions or explicit solutions without having to solve the PDEs. And that's what we have been mainly working on. And we use the direct method that was introduced by Professor Tyrone Duncan and his collaborators. So I summarize here the different steps we have in the direct method. So first of all, we have the mean field type problem. Then based on the structure of that cost and also based on the structure of the system dynamics, we have to propose a guess functional. So we have there a problem because we need to find an appropriate guess functional. But there are some cases in which this can be made easy, but in other cases, it might take longer time. Then with this guess functional, then we apply Ito's formula, and then we can identify those terms that are depending on the control input. So with these terms, depending on the decision variable, we can optimize. So in the quadratic case, we have a square completion. but in general, we have a terms completion because this can be applied to nonlinear cases as well and non-quadratic problems. And then after doing that, we can make conclusions about a semi-explicit solution. So as you can see here, the main ingredient of this method is given by the ethos formula. And then other type of stochastic processes beyond Brownian motions could be considered just by using the appropriate ethos formula, depending on the problem we have. Now, this is an example of a quadratic mean field type game. So the important thing here is that in the quadratic case, we have risk terms in the cost function. And we have more specifically the variance of the system states and the control inputs. So what we're doing here is to find an optimal solution that minimizes the risk. In this case, the variance. But as I said before, we might consider other type of risk terms. And in this particular example, we consider a drift that is state dependent and control input dependent and mean field dependent. But in the diffusion term, for simplicity, we just consider this sigma zero. But it's important to point out that actually we can consider the state dependence and the control input dependence using the same method. So this is just an example. So what we want to do is to find a semi-explicit solution for this. So now let me show you an example, a concrete example in engineering to see the performance when we consider risk terms. So this is an engineering problem in which we need to manipulate the inflows in different reservoirs. And the objective is to do an even-handed distribution. So in other words, we want to manipulate the input flow such that all the levels get the same value. And we have a constraint given by the resource we have, in this case, is given by D. So in the first row, we have a mean field free control example. So what we mean by mean field free is that it's a controller that actually does not consider risk terms. So we are not minimizing the variance or other kind of terms. So we see that actually we managed to achieve the same level or at the same expected level. And we satisfy the constraint in this case is given by 6. But, and here we see the distribution of the variables of interest. So in the second row, we see now the mean field type controller. And in the same way, we have, I mean, we satisfy the constraint and we have the same expected behavior. So what I want you to see here is that if we compare the distribution of the variables of interest, then we managed to minimize, in this case, we had a volatility oscillating in a range of 0.5, and we could minimize it to be 0.2. And regarding the control inputs, we could also do the same job. So this is the idea, that we accomplish the same control objective, but at the same time, we want to minimize the risk. And on the other hand, we have the consensus problem. We have a consensus algorithm. So we have here some uncertainties regarding the opinion or the state of in the neighbor. So we can actually associate that with some malicious agents and so on. So here we see a mean field free consensus. So it means that we don't care about risk terms. And we see that we have a noisy consensus. So, and here we can see the distribution of these states. On the other hand, we have the mean field type consensus. And we can see that now the behavior has less oscillations around the consensus. And that's because we have managed to minimize the volatility that is associated to it. So in case we want to implement these kind of strategies, one alternative that I think is the most important one is to try to address these problems in discrete time. So this is a problem statement in which we have discrete time. And the good news is that we can use the same simple method to solve these problems. So we can use the direct method in its discrete version. And again, we can consider state dependent and control input dependence in the drift and in the diffusion terms, or well, the noisy part that we have in the difference equation and the part that is independent of the noise. And we can find this semi-explicit solution as well. So now I wanted just to discuss a bit about a new challenge we have in the field. This is an ongoing problem. So this is the map of Colombia, which is actually my country. So I want to show you here how we can estimate the propagation of the virus. So this is based on data, and later on in the next slide, I'm going to show you how we performed these simulations. So the important message here is that this is a simulation in which we consider the migration between different cities. So we wanted to show the importance of early decision. So if you make the decision soon, you can actually have control over it. But if you do it too late, you might have a lot of problems. So this is the map. In the orange dots are the infected people of coronavirus in Colombia in March. And then we could see the evolution of it till now, up to now. So we see that the blue dots are the recovered people and red dots are people who have passed away. And what we want to do is to incorporate into the model, because we have some models that consider susceptible people, infected, recover, and that. But they are independent on the location of people and the traffic that we have with flights and so on. So this was the first motivation to work on this. So there's a simple model, which is the SIRD. So we have the susceptible people. This is divided into two parts: the exposed people, actually, that those are who are under risk to get the disease. And we have incorporated here the people who are under quarantine. So we have the infected people that might to recover, or they might dead as well, and people who already recovered might be infected again. So the idea here is that these jam intensities in this Markov chain can be control dependent. So if the government impose some compulsory lockdown, what the idea is that this can be captured by a control input that is affecting this jam intensity. So we want to minimize, of course, people who are infected, but we can at the same time penalize this control input because it can be associated with economic crisis and stuff. So this can be modeled by using the Kolmogorov-Forward equation. And then we want to find a control input that could solve the problem. So as I said before, this was motivation to work on this. And this is an ongoing work. So there's a paper that I present here below. And then the idea is to consider in this work, the author considers to incorporate more states in this idea. So not only focusing on the susceptible people, infected, recover, and that, but also including more details into the model. So considering location, age, and pre-existing diseases. So here we can see that infected people can be at home, or they can be in special care in an intensive care unit, or they can be in a hotel because it's under a compulsory quarantine and so on. So this is an extension, let's say, of the model I presented before. And the idea is to identify the jam intensities that can be manipulated in order to minimize the risk to get the infection. And on the right hand, I present you the SEIR model, the susceptible, exposed, infected, and recovered model. And here we can see that if we group some states from this more detailed system, then we can retrieve what we can find in literature. So this is an option to study these kind of problems. And here, let me present you the Bogota city, which is the capital of Colombia. And then we want to study how the virus propagates, but considering the location. So here we see a graph that represents different states. So the yellow dots represents the transportation system, the public transportation system. And then Bogota is divided into 20 different locations. Localities is the name we use for that. So it's a cluster or a group of different neighbors. And then we can model people who are at home, and they eventually have to go to the supermarket to get resources and so on. So they actually are under risk when they do that. And here in the red dots, we have the infected people per locality. And with the purple, we model the aggregated or the most important points where people work. And all of these black dots represents the hospitals we have in Bogota. So the idea is to extend those models I presented to you before, but also incorporating the location dependence. So we want to model how people get under risk as they move throughout the city and so on. So hopefully in the future, I can show you the results of this ongoing work. So before finishing, I would like to acknowledge some of our colleagues. So people I work with in the team of the Learning and Game Theory Lab, Professor Hamidou Tambinea and Dr. Salak Shutri, my former advisors, Nicanor Quijano and Carlos Ocampo, and some people with whom I have had discussions in particular on mean-field type game. So I acknowledge them. And of course, I want to thank all the co-authors with whom I have had nice discussions. And I would be very happy if some of you would belong to, would be part of this slide in the future as well. So thank you very much. And I appreciate if you have some comments.
Thanks, Julian. If there are any questions, raise hands, ask. Okay. Daniel, you want to ask a question? Or? Yep. No. Igor, if you're okay, go
yes,
ahead.
If you allow me, just sorry for a trivial remark. Just if we move to slide 8. Sorry, yes, slide 8. Just I wanted to mention that that probably it will be relevant to emphasize that that this is not just the Fokker-Planck-Kolmogorov equation, which is linear with respect to the probability distribution, or more precisely, the probability density function, but well, rather it is indeed a partial integral differential equation, which is in general nonlinear because the drift and the dispersion terms are actual functionals of the current probability distribution. And maybe it would be relevant to mention, a correspondence with the so-called Makin-Vlasov equation, which is known in plasma physics, which is a literally bright example of mean field effects in systems in large systems of interacting particles. Okay, thank you.
Yeah, that's true. Yeah, actually, yeah, we can mention the type of Makin-Vlasov problems. So as you mentioned, when we have several particles interacting to each other. So actually that's the approach in which we have a really large number of decision makers. So that's like how we can make the match between the multiple particles we can have in the interaction with the number of decision makers we have. But yeah, certainly I agree with you, because that's important when we have the differential equation depending on distribution. So we have a class of Makin-Vlasov problems. Yeah. So here was the motivation that there's a class of problems that we can solve without having to go over these PDEs, because this can be really difficult to solve in the most general case. But we focus on some linear quadratic problems that we can solve in a semi-explicit way. So actually, the motivation is to try to avoid these problems that are really complex to solve. Sometimes we use numerics to solve it. But we want to define certain problems that we can solve by using the direct method. That we introduced afterwards. So this was mainly like a motivation that in general, these problems are really complex to solve because of these type of Makin-Vlasov equations. But we can have a class of problems that we can solve using the direct method. And the difference is in the solution, we get ODEs. So that's nicer in the sense that they are not that complex to solve. And on the other hand, those solutions that are semi-explicit or even explicit might help us to understand the numeric solutions we get when we go over this approach of PDEs. But yeah, certainly I agree with you regarding the most general problems with Makin-Vlasov type. Yeah.
Just one more remark / question. So I suppose that is tractable in the case when you have some sort of algebraic closure for the moments. If the dependence on the distribution is organized as a dependence on the moments. So instead of considering the evolution for the whole distribution, you restrict your attention to the evolution of relevant moments. And provided you have some sort of algebraic closure for them. Okay, thank you so much indeed.
I see, yeah. Thank you.
Nation?
No, thank you so much. Yeah.
I have a quick question myself. You mentioned that you can use other measures of risk, and that's a Pandora box talking about different measures of mix and risk and what they mean to different people, and people get into fight. But can you explain? So for variance, I understand why you use it, because it simplifies writing the equations. But what breaks down if you use these other measures of risk, like, I don't know, EVARs, CVARs, all these things that are considered as coherent risk measures?
Yeah. So the thing is that since we want to solve it in a simple way, let's say, so we want to use the direct method, right? So when we use other type of risk terms or other class of risk considerations like higher order moment, so it's more challenging to find the appropriate guess functional. So as you said, the variance, it's easy to handle because it has a specific quadratic structure that we are familiar with. Yep. But we have also worked on polynomial costs. And in that sense, we might consider other moments. And on the other hand, the other alternative is to use the risk-sensitive approach, in which we have also other higher moments. And those risk-sensitive problems, we can solve them in a semi-explicit way as well. Yeah. But yeah, certainly, as we consider other type of terms, it might be more challenging to use this specific approach that is simple.
Okay, thanks.
Yeah, thank you.
So if you have no more questions for Julian, we thank him again. Thank you very much. And thanks for your attention, everyone.
Thank you very much.
See you next week and the future talks. Thanks, guys.
Thank you so much.